It's our second video with integration resulting in inverse trig functions. This one's focusing on substitution, so make sure you watch the first video prior to this. And we basically have the integral of two examples: integral of 5 over 9 square root of 9 minus 4x squared. And one thing we can do first is to most of those trig equivalents, inverse trig equivalents, involve 1 on the numerator, so there's especially sine inverse and cos inverse do. So let's see if we can get it into the form (1 over the square root of a squared minus x squared). Take the 5 out the front. Yields this. Now this is where it differs from one from a video or two ago. We could take the factor of 4 out. Another thing we can do is use integration by simple substitution, and so we covered this previously as well. You might recall that we can let u equal something. Now we want the variable to be squared, so let's say let u equal 2x, because essentially we have 2x all squared here, and we can get a u squared which can take the place of that x squared. So du dx, following the process we use with substitution, and we've got du dx equals 2, or more usefully, du equals 2 dx. Okay, so if we write down what we want to see, we then have to work out how much we have to adjust by with a compensatory multiple to keep the overall value the same. So we've got a 2 dx needed. Now that 5's always there too. What we've done, if we have a 2 dx, we can replace it with du when we make the u substitution. That's coming up next, but we've just doubled the value of it essentially. So what we do is we need to multiply by a half, and now it's of the same value. The integral has the same value. So that's a process we've seen previously with substitution. So once the substitution is made, we can get this. Square root 9 minus, okay, so remember u is 2x, so 4x squared is u squared. Now we have the form that we were looking at for, with the u substitution doing some of the work for us there. Okay, so we have something in the form that we want, and we can then use our rule we've established over the last few videos, and that will follow sine, inverse sine. Now it is x on a in the standard form, so this will be u on, now a squared is 9, so a is 3. Plus c, and we have inverse sine. Now we make this substitution back in, u equals 2x, so we have 2x over 3, and that gives us the same result as the other method we used. So you have a choice. Substitution does get used in conjunction with other forms of integration. This one will have an integral with an inverse trig function in it. First thing we've got to do is complete the square, and then further into it we have to make a simple substitution. So completing the square, a perfect square starting off of x squared plus 2x would be x squared plus 2x plus 1, because that's x plus 1 all squared using our perfect square expansion. But it's not plus 1, it's plus 6, so we need a plus 5 there. So what we've done is complete the square, which is a must-know strategy if you're doing this sort of maths. Okay, so we've completed the square there, so we can rewrite this integral as. Now, if we think about that, we've got something squared plus something. There's no square root, so it might take the inverse tan form. So let's keep our minds open, our eyes open for that. So we write the answer down with the square completed on the denominator. Okay. Now, the relationship between a squared, which looks like it's going to be 5, and the numerator is not the same as what we've got here at the moment. So what we could do as an option, just to make things a little bit easier perhaps, or less cluttered, is to do this. Send the 2 out the front. Now we make the u substitution. So let u equal x plus 1. So we'll have u squared there as the variable instead of x squared. Du dx is 1. Therefore, du equals dx. That's nice and easy, isn't it? So wherever we see dx, we can replace it with du. So we have 2 times integral of u squared, 1 over u squared, plus 5. And du is a direct replacement for dx in this case. Now we write down what we want to see on the top. So on the numerator, if we have let a squared equal 5, a would be root 5, as so. So that means we need to have root 5 on the denominator. So write down what we want. So it fits the form we're chasing. Of course, we've multiplied the value of the integrand by root 5, so we must divide by root 5 to compensate for that. So it's 2 over root 5 out the front. Okay, so we have 2 over root 5, and that's times inverse tan. We have, following the form in green, u over root 5 plus c, and all we need to do now is substitute back for the value we had, and we made the substitution u equals x plus 1, so we sub back now to x plus 1 plus c.